we take the graph of y equals quantity x plus 1 squared, and we make a table using the usual x and y values. We're not going to bother with the negative 1/2 and the 1/2 because the fractions get bigger and it's not a big problem. But we don't want to think about what 5/4 means or 7/4 or anything like that, okay? So evaluating y equals quantity x plus 1 squared, well, negative 2 plus 1 is never mind, I was looking at something else. Negative 2 plus 1, as I say here, is negative 1. Negative 1 squared is 1. So we get 1 when x is 2. When x is negative 1, well, negative 1 and 1 add up to 0, as we say here, and 0 squared is 0. Similarly, we're going to get, when x is 0, we're going to get 1. When x is 1, we get 4. When x is 2, we get 9. And Peekaboo actually did pretty well with this. So I was somewhat pleased with that. Okay, well, and when you plot the points on this graph, you get this point, this point, this point, this point, and this point. Now, for comparison, I plot y equals x squared, because this is a whole lot like y equals x squared. We've just replaced x by x plus 1. So this is actually a composite of y equals x squared with y equals x plus 1. We don't really think of this as a composite, but it is. Oh, yeah, later in calculus you will think of it as a composite, but for right now, it's just this function, and you'll see where we're going with this. So, how does this graph compare with this graph? Well, every point of this graph shifted 1 unit to the left gives you the point of this graph, okay? Now, we have this point shifts 1 unit to the left, this point. And then we have an extra point up here that doesn't relate to one of the points that we get when we graph y equals x squared with our basic values, but it's a point that we would get if we evaluated y equals x squared at x equals 3. Okay, so the thing we demonstrate here is that all the points of the y equals x squared graph appear to shift 1 unit to the left when we replace x by x plus 1. Okay. Now, if we want to do a more symmetric graph of y equals x plus 1 squared, we say, okay, well, you know, we got our 0 when x was negative 1, so let's put negative 1 in the middle of our values, and let's use the values negative 3, negative 2, negative 1, 0, 0, 1. And see what we get. Well, you can verify if we plug in negative 3, we get negative 2 squared, which is 4. Negative 2 gives us 1, and so forth. We get our familiar values. I hope they're familiar, because I hope you've been spending a lot of time with these tables. You get 4, 1, 0, 1, 4. Numbers you get for an x squared graph. But now you get them for an x plus 1 squared graph by shifting all your x values 1 unit to the left, by shifting x equals 2 to x equals negative 2 to x equals negative 3, x equals negative 1 to x equals negative 2, and so forth. And now your graph is nice and symmetric, and it still agrees with what we did here. But now the graph looks just like the graph that you would get for y equals x squared using the basic values. Okay? Now we do the same thing for y equals x plus 2. We evaluate the graph, and we evaluate y at the usual values of x, omitting the negative 1/2 and 1/2, not because we couldn't evaluate them, because we just don't want to mess with the fractions right now. We can get the picture without having to do that, so we won't do that. Okay, well, when we do that, here are the y values that we get. We get 0, 1, 4, but we don't get the 4, 1, the 4 and the 1 that we got here. We start with 0, so we got 0, 1, then 4, and then we get 9 and 16. Now 9 we got over here, 16's new. Well, what happened? If we plot this, well, we get a graph that looks like this. Now we kind of expect that that's maybe half of a parabola, and it is, but let's verify it, okay? So what it looks like is, if we take the y equals x squared graph and move it 2 units to the left, this is what we get. And that would make sense because The x plus 1 squared graph takes the x squared graph and moves it 1 unit to the left. If it was x plus 2 instead, it would make some sense that it would move 2 units to the left. Well, let's see how that works out. If we move all our x values 2 units to the left, so that negative 2 becomes negative 4, negative 1 is replaced by negative 3, and so forth, we get these x values. And when we evaluate this function, and you can verify this, we get our 4, 1, 0, 1, 4 numbers again. Okay. And then our graph would include a point here and a point here. And it would be nice and symmetric, and we'd have a graph just like our blue graph, but shifted 2 units over. I've got a little different Y scale here because I want to get 16 into it, so the graph looks a little more squashed down. But if we graphed the x squared graph, we'd be here, and here, and here, and here, and here. This would be our, yeah, it'd be up here, but here'd be our x squared graph, which shifted 2 units to the left would be the graph of x plus 2 quantity squared. So we make a conjecture, and the conjecture happens to be true. We're going to conjecture that y equals x minus h squared shifts the y equals x squared graph h units in the x direction. Okay? Now let's just test that conjecture. You might not have made the conjecture if you were making a conjecture. You might not have made a conjecture at all, but if you were making a conjecture, you might not have written it out quite like this because you wouldn't quite yet see where all this is heading. You would conjecture, though, that if you did x plus 3 squared, well, that shifts the graph over 3 units, right, to the left. So then you might ask yourself, well, what if it's x plus 3 squared? Well, it probably shifted in the opposite direction, so shift it to the right. Anyhow, we get this. We have this conjecture. Let's check it out. For y equals x plus 1 squared, well, what would h have to be to get x plus 1 in here? X minus what equals x plus 1? Well, h equals negative 1 would do it. X minus negative 1 would be x plus 1. Okay? And h is negative 1, so that the x plus 1 squared graph would be x minus h squared for h equals negative 1. And the conjecture says it moves 8 units in the x direction, meaning it would move negative 1 unit in the x direction. And that's exactly what the x plus 1 graph did. So we make a statement. So y equals x plus 1 squared shifts the graph negative 1 unit in the x direction. Okay? And in general now, for any function f of x, the graph of y equals f of x minus h shifts the graph of y equals f of x h units in the x direction, just as it does for the x squared function. And that's because, just look at what we did with our x values. Okay? We moved the x values negative 1 in the x direction, and if we were evaluating some other function, we would have still done the same thing. Doesn't matter what function we're evaluating. Our basic points, our basic x values will move according to this rule. So you can think that through, and it takes a little sinking in, so I don't want to say too much about it right now. But that is the basis for this general rule. And the better you understand this example, the better you'll understand this rule. And the fact that x plus 1 squared moves the graph 1 unit in the negative direction.